here. So in this occasion, I welcome Dr. Joseph Gladwin, sir, IEEE APS Madras Chapter Secretary for this event. I welcome you, sir. And in this occasion, I should thank Dr. Shanmuganandam, sir, Chairman, IEEE APS Madras Chapter. He had given his full support for every proposals. I welcome. And I also thank Dr. Nityavadi of IEEE Student Branch Counselor of Kongu Engineering College. And I also thank our HOD ECE of Kongu Engineering, Dr. T. Meera Devi. And I also welcome Aakash Bansal, PhD researcher, Loughborough University, UK, our speaker. He is going to deliver the topic on 5G millimeter antennas. I welcome you, sir. And I also welcome all the participants who had shown their full interest in attending this webinar. Thank you. Thank you all.
Mr. Aakash Bansal is a PhD researcher at Loughborough University. He completed his BTech in Maharaja Surajmal Institute of Technology. He was a research associate at CSIR CEERI. His interests include microstrip antenna, phased array antenna, millimeter wave communication, SIW slot antenna, beamforming techniques. He has demonstrated history of working with the government-funded research organization and non-profit organization management industry. He is the head of innovation and student reach at National Indian Students and Alumni Union, UK. He is a STEM promoter. He had been a sub-zonal coordinator of IEEE Region 10 and been an industrial relations in IEEE India. He was the innovation coach in Connecting Dreams Foundation. He has a good number of great publications. He received various awards, which includes Electronics Weekly Bright Sparks 2020 Award. He is the recipient of MIT GSW Fellowship 2016 and recipient of IEEE Computer Society Richard E. Merwin Student Scholarship 2016. He also received IEEE Delhi SAC Outstanding Student Volunteer Award. Every thought you produce, anything you say, any action you do, it bears your signature. Now, let us invite our respectable chief guest, Mr. Aakash Bansal, to take over the session.
Hi everyone, thank you for such a humble introduction. Let me try turning on my camera. Yeah, hello everyone. So thank you first of all for having me here to let me present a little bit about my work, things that I've been doing over here. So is it okay if I share my screen?
The sharing is not yet started, sir.
Oh, the session hasn't started yet?
No, you have to share your PPT, sir.
Yeah. Can you see it?
No, sir, it's not visible. Yeah, now only it's started.
Okay. Is it visible now?
Yeah, it's visible, sir. You can go ahead.
Okay, perfect. Thank you. All right, guys. So, hello everyone. So, as they've already introduced me, my name is Aakash Bansal. I'll be talking about 5G millimeter wave antennas. A little about me. I come from Loughborough University. It's one of the top 5 universities in the UK, working in different areas. Wireless Communications Group is one of the biggest groups in the UK, working on different areas, including 3D printed lenses, microstrip antennas, millimeter wave antennas, antennas for 5G, metamaterials, and much more. Further, what do I do over here? I'm working on active beam steering millimeter wave antenna arrays. In very simple terms, I'm trying to change my antenna's direction without physically moving it. This is how I would describe it in a layman term to anyone. These are some of the snaps from the lab, the things that I've been doing for a while now. So let's come to the main session where what am I going to talk about? Before I start that, I just want to tell you that I will try to keep this presentation as brief as possible. I would prefer this to be a one-to-one session or a session where you guys can ask as much questions as you want, rather than just me speaking throughout the session, because at the end of the day, that is what is going to help you all. So I'll start a little bit about mobile communications till date, how it all started, where we are today, why are we looking at 5G, and when we are looking at 5G, why millimeter wave communications, what sort of problems we face when we work in millimeter wave communications, and what are the major design challenges. Then beamforming is one of the major techniques through which 5G is being enabled. What is beamforming? How is it achieved? Things like that. And then I'll end with a little bit from my research, what I've been doing, my antenna designs, and I'll be presenting a little bit more in that area. So let's start with the mobile communications till date. So the whole thing, the story started with 0G when the wireless communications was introduced publicly for the first time, and they were installed in police cars for the first time. These were huge radio sets which were installed inside police cars for wireless communications in the United States. This was the very first experimentation with wireless communication, and it only supported audio calls. It later on get to public from public servants. It shifted to public when Martin Cooper invented the very first mobile phone. The one thing that we called mobile phone because it was supposed to be carried around. They were huge. They were bulky. They used to weight. They used to weight equivalent to a brick. They were up to 2 to 3 kgs heavy. They were extremely heavy, and they only supported audio calls. The best thing were you can actually carry them anywhere, and you'll get a cell reception. Slowly the technology progressed further, and then we came to 2G. The messaging was introduced. We got a combination of both analog and digital communications. Till now, till 1G, everything was analog. Every call, the only network that is wireless is between your cell phone and your base station or a mobile tower, and then everything is wired. There used to be someone who used to patch you in with the correct contact. When 2G was introduced, a little bit of data communication came into picture, digital communications came into picture, and people were allowed to send in SMS, short messaging services, connecting the world with 160 characters. This is when Nokia boosted with their heavy duty phones that we just throw away and nothing used to happen. This is, I believe, most of us would remember. Most of us may not even remember Martin Cooper's heavy duty phones, but these are the ones that we started using for the first time. At least I did. And then came the era of smartphones. The very first iPhone was introduced with 3G. There were more stages in between, known as 2.5G and 2.75G, but they were not very prominent. The most common that is known among the common population is 3G. It was a hybrid network of both analog and digital communication. This was the time when mobile apps started becoming a thing. iPhone was introduced. Smartphones started to become something very common. This is when people started getting addicted to their phones. And now this is where we are today, 4G, converting everything from analog to digital communications, even the calls that used to be analog till 3G, with the introduction of voice over LTE or voice over long-term evaluation or voice over internet protocol, VoIP. Even the calls started happening over digital communication, over internet, over data. And 4G is at present the maximum internet speed that we have. We have extremely fast internet. We have movies which gets downloaded in matter of seconds. Um, if we already have this strong internet connection, this strong data communication, the major question that comes up is, why do we need 5G? What is the need of it? And when we talk about 5G, we are looking into millimeter waves. Why millimeter waves? Why 5G? So to answer these two questions, the current state, we need to look at the current state of mobile communications. The very first and the most important thing that you need to know is there are more than 6 billion users presently. By 6 billion, I mean 6 billion different devices connecting to internet every day. And this number is increasing. And it is assumed to be thousandfold by next few years, which is going to be very for antenna designers or for communication engineers. It is going to be a challenge to add on so many devices altogether, which can support the same internet connectivity, which can use the current infrastructure and still work perfectly fine. We currently, whatever communication happens, it is at microwave, it is below 3 gigahertz. We use Wi-Fi at 2.4, we used GPS and other GPRS, GSM, everything at 1.8, 900 megahertz, 870 megahertz. These are all below 3 gigahertz. We have recently started using 5G. Recently started using 5 gigahertz Wi-Fi as well, but this is quite frequent. Let's stay below 3 gigahertz. But as the number of devices increase, as we all know that these frequency bands are further divided into smaller channels when provided to every user. Now, if the number of devices in a particular area is increasing, the number of channels will start to deplete. We won't have enough channels to provide service to every person who's looking for an internet connection or a connectivity with base station. That is why the bandwidth has started becoming an issue. The amount of speed that is being divided into number of users, and with the introduction of new technologies like Internet of Things, it is going to introduce millions of more devices every day which are connecting to internet. Self-driving cars, they need internet speed with almost zero latency, because even if there is a lag of 1 millisecond, a self-driving car can end up in an accident. Vehicle to vehicle networks, machine to machine communication, everything today is connecting to one sort of network or another, and everything is being connected to internet, which basically requires a much higher data rate and a lower latency. That is why there is a requirement of 5G, and that is why, because of lower bandwidth and the overcrowding of frequency bands till 3 gigahertz, we have started looking at higher frequency bands and how we can consume a higher frequency band for the use of so that the designers, the network engineers, and everyone can plan out a network with the ability to support the same thing for next few decades. Coming to the definition of 5G, this is how Office of Communications in the UK and FCC worldwide defines 5G. 5G is the next generation of mobile technologies and is being designed to provide greater capacity for wireless networks, offer greater reliability, and deliver extremely fast data speeds, enabling innovative new services across different industry sectors. This is a more formal definition of 5G. Let's come to a much more simpler one. This is how Dr. Wong defined it, or how I would define 5G. 5G while millimeter wave communication is to connect the entire world and achieve seamless and ubiquitous network between anybody, which is a people-to-people network, anything, people to machine or machine to machine network, wherever they are, which basically means the connection should be available anywhere on the planet, whenever they need. It should not be dependent on time. It is available 24/7 by whatever electronic device, service, network they wish to. That basically means it does not mean that it will only connect to your mobile phone or your laptop. It can connect to any device in the world, anything which has a wireless network capability, it can connect to this network. This is how a simple 5G definition comes across. Now, the main question is, we have been looking into different spectrums. Right now, 5G is under test stage at in various countries. Over here in the UK, 5G is being tested in 10 different states, 10 different cities, and I think they've recently started in 2 more cities. But everything is being happening at something we call sub 6 gigahertz, which is from 3.4 gigahertz to 3.8 gigahertz. This is slightly above the microwave frequency band, but still not very high. So the probability, because we do not have a huge bandwidth, as we see, it's only 400 megahertz. The probability of it being consumed very quickly is very high. That is why we're still looking for a much better frequency band, and that is why we jump up higher to other frequency bands like 24.25 to 27.5, which we commonly call 26 gigahertz band, similarly 28 gigahertz band, 38 gigahertz band, 48 gigahertz band. And then there's another one which is called 60 gigahertz band, but that is something which we are looking for much further in the future. Now, the main question is, why are we jumping from 3.4 to 3.8 or sub 6 gigahertz to directly 26 gigahertz? What about the band in between? Why aren't we not looking from 6 to 26 gigahertz? Why are these bands not consumed? So the very simple reason behind it is the attenuation, because of the propagation losses that a signal faces when it travels through the atmosphere. So basically, all these communication networks have already been established in an indoor environment where there's a router in the room operating at 28 gigahertz or 30 gigahertz or 60 gigahertz and is producing signal all around within the building. It's an indoor environment. But when we go outdoor, there are a lot more things. There are things like other buildings, obstacles around, vehicles around. There are issues like rain, water droplets, oxygen, other molecules, atmospheric molecules, which introduces a lot of attenuation in the signal. So there was a particular study which presented that we face a huge loss in specific frequency bands, in almost all the frequency bands above 3 gigahertz, due to which those are not usable for a practical mobile network. But these specific frequency bands, the ones that are being mentioned over here, are the ones that were identified to have a much lower attenuation and propagation loss, which can practically be used for a mobile network. So for example, over here, you see that attenuation due to rain and due to atmospheric absorptions, it is 0.012 dB at 28 gigahertz and 0.016 dB at 38 gigahertz, which is very, very low. Similarly, for rain, it is 1.4 dB at 200 meters at 28 gigahertz, but for other frequency bands, it is going to be very, very high. So what are the solutions that, again, 1.4 dB at 200 meters is very high, or that means at 1.5 kilometers, it is going to be 3 to 4 dB, which is a significant loss, and we cannot afford this much loss. So what are the solutions for it? These are some of the challenges that we face. So some of the major challenges behind millimeter wave communication is, as we go up higher in the frequency, our wavelength reduces, and as the wavelength reduces, the aperture size of the antenna, the size of the antenna, or the aperture of the antenna, it reduces drastically, which basically affects the gain of the antenna. But there's a simple solution to it. If you have smaller antennas, we can create a much larger array, which will eventually improve your gain. So in a smaller area, you can have a much larger array compared to the one which we used to design for 1.8 or 2.4 gigahertz. The same array would be 5 times or 6 times much larger than that one at 28 gigahertz. Similarly, looking at the penetration and absorption losses, penetration losses because there are buildings, or there are molecules like water molecules or oxygen molecules, which are basically resonating at different frequencies, and they're going to absorb those particular frequency bands. So we study about what sort of absorption they're going to present. So for example, the oxygen molecules are going to present up to 15 dB per kilometer of absorption, which is very high. But a very simple solution for this was to create much smaller cells, which are known as picocells. So when you look at a mobile tower, it basically provides network in a specific area. That region is known as one particular cell. So every tower caters one cell at a time. And in current 3G or 4G network, these cells are from 1.5 kilometers to 2 kilometers large in radius. The idea is to reduce these cells to picocells, much smaller, at which will be like 200-meter radius, so that the losses can be covered and everyone can be. So when the cells are smaller, it can. So one cell that is treating 1.5 kilometer large radius and another one treating 200-meter radius. Obviously, the 200-meter radius one will have much lesser people compared to the one in 1.5 kilometer. So this basically helps you provide service to more people in a smaller region altogether. Now, as we know that with the introduction of other technologies, the number of devices are going to increase drastically, and if we have smaller cells, we will be able to provide services to all those devices in those smaller areas quite easily. Apart from it, we have fading and delay spread, the amplitude changes, which introduce further phase delays, and it creates multiple signal paths, which becomes very difficult to recognize which one is higher loss, which one should be considered, which shouldn't. These are some other problems, and one of the biggest and the most rumored one are biological considerations, how much millimeter waves affect human body. So these are some of the major concerns that people have while talking about millimeter wave communications for 5G. This is a basic representation of how a base station is being planned for 5G millimeter wave communication. It's basically what currently happens is a base station basically radiates out a signal in all the directions and look out for the receiver signal. So if I'm sitting over here and there's a base station 700 meters down the road, it is going to radiate a signal for 1.5 kilometer radius circle, and it is going to and let's say you're calling me, so it is going to look for me. My mobile receives that signal. It identifies that it is looking for me, and it radiates back and says that yes, I'm here, and then it builds a connection with me. So right now, one single antenna is covering a specific sector. It is approximately 60 degrees. So the whole there are basically three antennas. If you've ever seen, it's a triangular structure, each covering 120 degrees, and that continuous radiation is further divided into smaller frequency spectrums. But in millimeter wave communication, the idea is instead of having one antenna or a single antenna array which is providing a beam of 120 degrees, what if we have smaller beams which are catering one user at a time? So for example, if you look over here, this green beam, these are the beams that are going to cater every person at a time. So if we're going to produce so many beams at the same time, it introduces two very interesting concepts. Number one, beam steering or beam forming, and number two, multiple input, multiple output systems. So this basically means an antenna has to produce multiple beams at the same time, and it should have a capability of keep on steering the beam from one direction to another so that it can keep on looking for everyone. Otherwise, if there's one constant beam in one specific angle, it is not going to look for users in other directions. It is going to be a problem. So that is why these two terms, beamforming and MIMO, are said to be the key enablers for 5G. And we're going to discuss more about beamforming ahead. So these are the basic requirements that have been identified for mobile stations and base stations. So the transmission power is supposed to be more than 40 dBm for base stations and 23 dBm for mobile stations. The beam steering for base station is said to be at least 30 degrees in horizontal or azimuth plane, and at least 10 degrees in elevation plane to cover the people on specific heights. On mobile stations, it is assumed to have a whole 90-degree beam so that it can cover a larger area. Further, the total gain that for a base station antenna is believed to be should be more than 25 dBi, while for mobile stations it can be greater than 12 dBi. Looking further, so the proposed techniques for these sort of antennas. If I just a second, if I look at this, these sort of antennas are also termed as something called smart antennas, because they know what beam to be, where to transmit a particular beam, how to find a particular device. All these capabilities are installed within the antenna. So these smart antennas are proposed to be designed using three different techniques: beam switching, beam steering, and MIMO. We're going to look at beam switching and beam steering in more detail over here. I'm not going to go into MIMO because a beam forming antenna can be converted into a MIMO further. By adding more elements to it, which are controlled independently to produce multiple beams at the same time. So I'll give you a basic introduction about MIMO and how it works, what sort of antennas are being developed in that area. But my major focus is towards beamforming antennas and how we reconfigure an antenna in a way that it can produce multiple beams, and it can scan. It can use one particular beam, a pencil beam or a very thin beam, and it can scan at different angles. So beam switching, it's a very simple concept. Beam switching is the most simplest form of beam forming. It's basically we have a huge array of antenna, each antenna being radiating at a different angle. We know which antenna radiates at which angle, and we just used various switches to turn on or turn off a particular antenna, and through which we can detect which direction should we transmit to. So these are simple representations on how it can be done. So for example, it's a switch, and you see there are three switches over here and four antennas. And using the combination of three switches, we can figure out which particular antenna is being powered on and which one is powered off. And each of the four antennas are radiating in four different directions. So you can decide what direction are you going to radiate in. Similarly, it's another form of the same technique. It's called a linear switch, where the signal passes through and it then divides into three different sections, either to an antenna or a ground, or it passes to the next antenna. And similarly, you can select whatever antenna you want to radiate from. And each antenna is being radiating at different angles, and you can find out what angle you want to radiate at. One of the biggest issues is with these kind of networks, with beam switching, is you do not get to know what angle the receiver is at. So for example, when we talk about mobile communication, it is never a one-way communication. It is always a two-way communication. So the antenna figures out that mobile phone is in that direction, but mobile phone never gets to know what direction the transmitter is. So or the base station is. So mobile phone will never know what direction is the it is called AOA, arrival angle of arrival, and it will never know what angle of arrival is. So it will not know what direction it needs to radiate to. This is why beam switching keeps on failing in terms of a mass production or in terms of a practical mobile communication network. So yeah, again, these are the same things that I just tell. That is why we we came to something called beamforming or beam switching. In simple terms, beamforming is a method of concentrating RF energy from an antenna in a particular direction. So there are different ways of achieving it. One of the simplest ways is using reconfigurable antennas, pattern reconfigurable antennas. But the most easiest or the most simplest way using electronic circuits is using a phased array antenna. So if the phase of an antenna is changed, the phase fed through an antenna, like if we have a huge array of elements, and if I feed the same signal but with specific phase delay to each element, my beam will start bending in a particular direction. To represent it in a more simpler way, over here you look at it like we know there are multiple elements. Now this one receives the signal first, the second one receives after a particular phase delay, let's say phi. The second one receives at a delay of 2 phi, third one receives at a delay of 3 phi, and so on. So this one radiates out a signal, the other one radiates out after a particular delay, second one after another particular delay. And overall, as you look over here, the overall wavelength that is created is bent at a particular angle. So using the same technique with the change in phase, we can basically control what particular angle do we want to radiate our signal to. Now, one of the major problems with these sort of phased array systems or beamforming systems is these require heavy phase shifter equipments. We're going to place heavy phase shifters with each antenna so that we can control the phase shifting for every particular element to control the beam steering, right? But as we just discussed that 5G is looking into creating picocells where we're going to have one mobile tower every 200 meters. And we already know how many rumors and how many uncomfortable people are there about 5G. So the system has to be as small and compact as possible without affecting, without having heavy equipments lying in front of people and just scaring them off that why there's a huge base station outside my home, it's gonna scare my children or anything. These are local concerns that we regularly see among people. So that is why heavy phase shifter equipment is one of the biggest problems, and this is why beamforming is being researched further to find much simpler ways. So these are now I'm going to present a few of the works that are being presented into literature on how beam switching is achieved by different people worldwide. So this is one of the very interesting works. It's one of the simplest form of beamforming or beam switching that I've seen in my life. So it's like this is one antenna element with 3 patches, and these are the transmission line with the black lines being switches or diodes, pin diodes. And using a combination of diode, you can define which path my signal will follow. So let's say if I turn this off and turn this switch on, my signal will pass through this, feeding this particular antenna, going straight either this way or this way, depending on how my switches are turned on. Based on the length of what the signal follows, the phase difference changes. So for example, if my antenna goes in here and passes through here, it doesn't travel a lot through the transmission line. But if it goes all the way up here and then comes by rotating all the way from here, it's going to follow a much larger trajectory and hence introducing a much larger phase delay. So through this, I can basically create different phase delay in 3 elements. And using that phase delay, my beam gets bent at a particular angle, as explained earlier. So this is how a very, very simple form of electronic beam switching is being achieved over here with simple patch antennas. Again, as this whole design is at 28 gigahertz, so you can see how small the structure is, how small each element looks. And it basically uses four different antennas, each containing 3 elements. So this is why there are 4 connectors connecting to each element, controlling each one with a different phase shift. This is another very interesting form. A lot of my work started from the introduction of this paper. When I went through this paper, this is where I got my initial idea from how I'm going to design my antenna. So what this is it's called an SIW, or a substrate integrated waveguide, with with slots in it. So each slot acts as an independent antenna, and being multiple slots is called, it is known as SIW slot array antennas. So you see there are 15 slots as represented over here, and what they did was they placed small surface pin diodes on top of it. So what surface pin diode does is, if you power them on, the whole slot acts as a covered copper sheet, and the moment you power them off, they act as an open slot. So if you power them on, it acts as a shorted circuit. If you power them off, acts as an open slot. So using that, they controlled which particular slots will be opened at a particular time and which particular slots will be closed. Using the same theory, they created different combinations through which the beam was able to steer in different directions. So as you see over here, they basically steered at 0 degrees, plus minus 30 degrees, and plus minus 45 degrees, presenting 5 different beams from a simple antenna at 28 gigahertz. This was one of the most interesting works that I felt, okay, this is something very interesting, and this is something people can explore further. When I talk about a little bit about my work is also dependent on SIW antennas, so you'll see how much relatable it is. It's not very relatable, but yeah, the idea initiates from here. Then this is another very interesting thing where we use frequency selective surfaces on top of an antenna. So over here, if you look at it, the gray is the ground plane, then the material, and then the source antenna, or any sort of antenna. And at the top, after a particular gap, they've put a reconfigurable frequency selective surface. So frequency selective surfaces are electronically designed. They're printed over a PCB material or any substrate as a normal, as the way we print a normal patch antenna. And they basically put switches on, and those switches control what frequencies are allowed to pass through this sheet and what frequencies are not. So if you look at it, these are divided into 4 sectors: number 1, number 2, number 3, and number 4. So controlling which part is powered on and which part is powered off, it basically sets 2 different frequencies. So for example, this one was designed at 5.5 gigahertz. So the FSS, if the switches are powered on, that particular section will allow 5.5 gigahertz to pass through it. If powered off, the frequency falls down and it doesn't let 5.5 gigahertz pass through it. That is the basic idea. To make you understand better, just assume there's something radiating, and you put a sort of filter on top of it, which have 4 sections on it. If you take one lid off, it lets the signal pass from that particular direction, but stops the other 3. If I put another lid off, it will let the signal pass from that direction, another 3 powered off. That was the basic concept, and using the different combinations as we see over here, they basically presented different beam directions, beams being generated in different directions, and hence another technique of presenting beam steering without the use of heavy phase shifters. Further, this was another one which uses reconfigurable cantilever FSS. Cantilever basically means it's a different concept where if you see carefully, these copper strips are basically lifted up slightly, and when they're pressed, they're electronically pressed with the help of specific electric fields around them. When they're pressed between the ground plane and the space between these reducers, the capacitance changes, and as the capacitance changes, the frequency that this frequency selective surface lets pass changes, and hence the antenna placed behind it will either let the signal will either pass through it or will not. So if I put, so what they did was they put a DRA antenna at the center and covered it with a complete array of similar frequency selective surfaces all around. And now if I select any particular area, so for example, if I select this area to be able to radiate, but none of the others are. So for example, at number 3, I'm just using these 2 elements and everything is powered off. My beam will come out in this particular direction, which is slightly lower and in this particular angle. If I power on the middle ones, it gives me a straight beam at the middle. If I power on the top one, it gives me another beam at the top at angle 3, and so on. I can basically select which FSS to power on through, which FSS my signal will pass through. And accordingly, I can select how my antenna is going to radiate. Another similar design was presented over here. It again uses the same concept, the cantilever arms. And as you see over here, the three particular beams being represented, and the three are being produced in three different directions. The most interesting work, again, this is the second thing that inspired my work slightly. So what they did was they used metamaterials. So people who do not know what metamaterials are, these are artificial materials which can be created in a lab with simple fabrication processes, and they basically represent. If you measure the permittivity and permeability of the material, they represent a negative permittivity and negative permeability. This is practically not possible, but theoretically we do get a negative value. And using the same, we can basically let the beam to bend in a particular direction. To understand it better, let us see if we have this particular antenna, or instead of having this particular antenna, let's consider a point source transmitting a light signal straight in the front. And we have two glass slabs attached together, and one of them have a different refractive index compared to the other. So my beam will start deflecting in the direction of the higher refractive index while going towards the lower. This is the similar concept. So if I see there are two materials over here, this one has a slightly higher refractive index compared to this one. So my signal will start bending towards this particular metamaterial structure, and hence my overall beam starts to bend towards the metamaterial structure. Using the same concept, the same authors, Dadakpur, what they did was they created an array of frequency selective surfaces. They're basically metamaterial structures. They're placed in front of four different monopole antennas, and they basically what they did was they kept on moving the monopole antenna, the position of monopole antenna compared to the metamaterial, and they produced different beams which are radiating at different angles. Basically using the same concept that if I keep on changing the position compared to the metamaterial, it's going to be higher refractive index at one corner and lower at the other, and my overall beam will start bending towards the higher one, and hence I'm gonna get different frequency bands, different beams at different angles for the antenna, depending on the antenna's position. Further, again, this is the same concept. These are called metamaterial lenses, where we stack a lot of them together, and the dielectric constant or the permittivity of the material is very low in this area, but as we go down over here, it tends to go very high, and accordingly we can steer our beam by placing an antenna closer to it. So these are various concepts that have been presented in terms of what beam steering is in its current state and how it is being explored further. I'll present a little bit about what sort of work I've been doing and how my antenna is presenting a beam steering antenna or a beam forming technique. So the idea, what I'm working on is an antenna array at 28 gigahertz and neighboring bands with beam steering capabilities without the use of heavy phase shifters or loads of active equipments on board. So my antennas basically do not use heavy phase shifters, and they try to keep the load of active components as less as possible. And instead of using heavy phase shifters, I use traveling wave antennas, which present a phase shift with slight change in frequency as well. So there are basically two types of antennas, either a standing wave antenna or a traveling wave antenna. A standing wave antenna is basically various, if there are multiple elements, let's assume there's an array of elements, the four elements, and my signal keeps on dividing into four different elements. But it's equal, the signal is being divided equally among the four. In traveling wave antennas, it's like if we have a series of antennas placed together, the first one radiates some amount of power, reflects back some amount of power, and refracts some further in the other direction. The refracted amount is received by the second antenna. It again radiates some amount and sends some further. And hence, each antenna keeps on receiving some smaller portion of the left out power from the previous antenna. This is what, in simple terms, is a traveling wave antenna. And since every element is receiving the signal after a particular phase delay, every element is going to have some sort of phase delay, and my beam will start bending in a particular angle. So this is this is the preliminary design of my antenna. It's a substrate integrated waveguide slot array antenna with 16 slots operating at 28 gigahertz and is fed through microstrip antennas and does not use a heavy waveguide feed. It uses simple SMA connectors at the bottom of it, and which basically feeds the whole structure through a pin. A pin basically passes through, goes inside the waveguide and puts a signal in, and that signal basically travels throughout the SIW. To make the work more interesting, what I did was I put a waveguide, I put a lens, a 3D printed lens in front of it. So this is how a 3D printed lens looks. Each color represents a different fill density for a 3D printed structure. So for example, we use PLA or ABS materials. They have specific dielectric constants or permittivity. Fill density is basically when you 3D print something, you have to specify how much density do you want for the material to have it. If you're going to put a very high density material, it is going to weigh very much and it is going to take a longer time to print. If you put the density to be very low, the weight will reduce and proportionally the time will reduce as well for the printing. So the center one, for example, over here is 100% fill, then 80%, 60%, and 30%. Using this, with the change in fill density, I can change the permittivity of the material. So this is basic lens theory. What I used is, I know that at the center, since I'm using 100% fill density, the dielectric constant is going to be 2.7, at 80% 2.4, and so on. So I know the different fill densities all across, and I know that the signal coming out from my antenna, the electrical length OB dash has to be equal to OA plus AA dash. So equating the two, OB plus BB dash and OA plus AA dash, I can basically figure out what should be the thickness of my lens and each particular element. Accordingly, I can basically 3D print my whole lens and see, I can basically 3D print my whole lens and can place it in front of the antenna. This basically helped me improve the gain because SIW generally have a very high beam width, which needs to be reduced further. With the lens, the whole beam focuses at one particular angle instead of spreading throughout, and hence it improves the gain of the antenna. So the features of my antenna are basically, it's a highly directional with low side lobes, 16 slot SIW. It presents a directivity of 21 dBi with an efficiency greater than 75%. For a band from 27 to 30.5 gigahertz, approximately 4 gigahertz band. It presents a half power beam width of 6 degrees, and it uses microstrip lines to feed the whole antenna, which is something new because we used to use to feed SIWs. We generally use waveguide structures, which are very difficult to place together, and it is very small in size. The overall area of the whole antenna is 4.48 centimeters square. So this is the S parameters for my antenna, and as you can see, it is an approximate 4 gigahertz band starting from 27 till 31 gigahertz. It's a minus 10 dB band, which is really good for the whole operation of the antenna. This is the efficiency. It is approximately 80% from 27 till 29.5, which is, and it still keeps staying high. It doesn't go down till 31. So the efficiency is quite high, and this is not just based on simulation. This is also based on the fabricated versions because during simulation you have basically two options. You can either define everything in an ideal condition where you use a perfect electric conductor instead of an annealed copper structure. You can use a perfect material. Over here I have used Rogers RT5880. There are two options, either a lossless one where it doesn't introduce any sort of losses, or within simulation there's another option where you can put a lossy one and it incorporates the losses that the structure is going to have because of the substrate. So considering everything, I was able to get a total efficiency of about 80%, both in simulation as well as in measurements. This is how the directivity of the antenna looks like at 27 gigahertz. It's a 20.76 dBi directivity with a gain of 80%, which makes my gain to be almost 19, almost 19 dB. Further, it's a 1D representation of the same 27 gigahertz presenting 21.1 dB at a particular angle. The most interesting thing is, okay, this is the radiation pattern for the fabricated version of the antenna. which is basically presenting the beam at approximately the right angle, and the results basically match with the simulation. The most interesting part is if I look over here, these are basically radiation pattern from 26.5 to 30 gigahertz with zero point 0.1 gigahertz shift. So for example, the very first line is at 26.5, the next is 26.6, 26.7, and so on. The interesting part is to see that each with the shift of 100 megahertz, my antenna basically shifts to a different angle. It basically represents the beam is being my beam is steering from one particular angle to another. This whole steer is approximately 15 to 20 degrees long with a single element, and hence if I put in three elements together, I'll be able to achieve a beam steer of 45 to 60 degrees with four elements. So this was the main concept at the end of the day, where I can put in multiple elements all together, producing one central beam. This is without the lens, and hence the directivity is 13.06. When I put the lens in front, it goes up to 22 to 23 dB, which is very close to what I initially defined, which was 25 dBi as a standard requirement. Since it is producing a 23 dB gain with the lens, which can act as a radome at the end, it can be considered as very close to the requirements. This is one of the fabricated structures of the same antenna. Yeah, this is what I'm doing right now. These are the further developments. I cannot present these in details at present because a lot of this work is still under writing and will be publishing it very soon. So I've created a 3D printed lens, much better structure than you see over here. So yeah, this was at the very preliminary stage. Right now, my whole lens has a very interesting structure, and it's a homogeneous structure. It doesn't use different field densities at different points. Rather, it uses a single field density throughout, which makes the structure more innovative. Further, the gain and directivity of the antenna has been improved to right now. I believe I just finished one measurement yesterday, and I had a gain of about 28 dBi, which is much higher than the standard requirements, and hence the gain is assumed to be much better. Then I've already tested SPDT switches, where basically these four antennas are controlled using SPDT switches. SPDT switches are basically similar to combination of pin diodes, which it's a chip. It's a small chip which basically decides if the signal is coming from one port, what port will it go out from, port one or port two. SP40 decides the signal comes in from one port, what port it will go out from, first port, second port, third port, or fourth port. And similarly, SP5T, SP60. I'm going to use SPDT over here. SPDT basically means single pole double throw. SP3T is a single pole triple throw, SP4T a single pole four throws, and so on. So yeah, this is what I've been working on recently, and this is what we're going to produce at the end of this year, most probably, where our antenna is going to have a 28 to 30 gigahertz, 28 to 30 dBi gain with the beam sharing capabilities of 0 to 60 degrees, and hence meeting all the requirements of that have been defined in the beginning. So I think I took about an hour to finish this. Yeah, this is all from my side. I would love to have some questions from your side. If you want to find out anything, if you have any specific questions, I'm happy to answer. See, one question, what is the difference between MTM and FSS? So metamaterials and frequency selective surfaces, I would say frequency selective surfaces can be considered as a subset of metamaterials, sort of, but FSS were there for a very long time. Metamaterials were discovered later on. But turns out frequency selective surfaces can be considered as a subset. So they're not very different, but in a way, frequency selective surfaces does not have to present a negative permittivity or negative permeability. Rather, they're simple structures which basically acts as a high pass or a low pass filter, allowing a signal to pass through it or not. While metamaterials, they basically themselves act as a substrate. You can basically consider them as a substrate and print your antennas accordingly. No problem. Any other questions? So I personally prefer to use CST, but I have used HFSS as well. It's a good simulator. The major difference is the simulation algorithm. One of them uses FEM, the other uses FDTD. I prefer CST because it is more user friendly. The design process is quite simpler compared to HFSS. But I've also worked on tools like ADS. I've been using Microwave Office and Empire. Empire is basically from Germany. It was designed by TU Dresden. It's an independent tool. You can look into it as well. I think we can look for. Do you have any other questions? It also falls in UWB frequency band. How can we differentiate those? It depends because UWB frequency bands. To answer it in a much easier way, there's something called a licensed frequency band and unlicensed frequency bands. When we work on ultra wideband antennas or UWB frequency bands, if you have seen that there are a lot of works where we basically scrape off some frequencies out of it. It's a separate area within UWB where we basically skip particular frequency band but within UWB because those are licensed frequencies and we cannot use them. So sub 6 gigahertz, yes, they do come under UWB, but that doesn't mean that they cannot be used further. Right now, most of the spectrum over here is unlicensed at millimeter waves. At sub 6 gigahertz, it have already been licensed to a lot of companies. You can still do a lot of research. There are open bands. They are known as ISM bands. For example, 2.4 gigahertz, 5 gigahertz, all these are ISM bands at which any person or any researcher, any scientist, any engineer can do any sort of test. They're allowed to use these bands, but the license bands are paid and no one can actually use those. Any other question, guys? Meanwhile, if you want to connect with me, I've just put in my details on the screen. I'm happy to connect with people who are working in this area or want to talk further after this session or anything. Frequency selector surfaces, as I presented, like there have been some research in this area. Just a second. Just a second. Yeah, so as I presented it over here, frequency selector surfaces can also be used for beam steering in this using these particular techniques. These are frequency selector surfaces basically. And when you look at reconfigurable antennas, there is one particular area of reconfigurable antennas known as pattern reconfiguration. Beam forming or beam steering is basically in a way pattern reconfigurable structures where we're basically reconfiguring our pattern to bend at a different angle. There is no best efficient way really because every technique has some sort of merits and demerits. So it depends a lot on what your application is and what are you looking at, and accordingly you can decide what antenna will suit more for your work rather than others. Satellite communication. So one of the biggest issues with satellite communications is it needs to have antennas with very, very high gain. Earlier, we used to use huge dish antennas in simple terms, but there have been recent developments where dishes are being constructed with various microstrip patches all around. So this is we use a huge array of antennas in terms of satellite communication because the distance of communication between transmitter and receiver in a satellite communication is much larger. And you need to decide how your antenna is going to be positioned. It is going to stay at a particular angle depending on the trajectory of your satellite. There are a lot of things incorporated when you look at modern antennas for satellite communication. SIW at 6 gigahertz, scope of research on SIW and 6 gigahertz. So when you develop a substrate integrated waveguide, it depends, the width of the waveguide and the length of the waveguide, it depends on the frequency of operation. 6 gigahertz will have a much higher wavelength. Your antenna will end up being very large, not too large, but in terms of it will be comparative to a size of microstrip antenna. It's a considerable area. You can always explore it and see how different what new can you introduce within SIWs at 6 gigahertz. There have been some work done in this area, so you can read about it. You can see how beam steering is being achieved in SIWs at 6 gigahertz as well. I believe that the work that I presented in this one, they also had a section which was particularly dedicated to SIW at sub 6 gigahertz range as well. So one of the major concerns is when you prepare something, it's good for research, but when you look at the practical demonstration of it, when you plan to actually put it in base stations, the size, the structure, the area that it consumes, and the control structure that is required at the back of it, it becomes a major concern. And we as designers have to take all these things into consideration while at the very beginning stage. Otherwise, we can prepare an amazing design with a huge aperture area, but at the end of the day, if it is not practically feasible, it's not going to be of any use. So I would recommend you to look, it obviously has a great scope, SIWs for sub 6 gigahertz. I would recommend you to look into what sort of requirements there are, what sort of work is being done right now, and what sort of antennas are being used at sub 6 gigahertz right now for different testings. Oh, the how to minimize the difference in simulation and practical measurements. So yeah, this is a very interesting question, and it is one of the most important things. So first of all, when you design the whole environment within simulation, either in HFSS or CST or ADS or COMSOL or any other simulator, I would recommend you to create an environment as practical as possible. So for example, within CST or HFSS, I know both of them have these features where instead of using a perfect electric conductor every time instead of at every conducting portion, use a copper with some sort of losses incorporated in it, because you're not going to get a perfect electric conductor anywhere. This is one of the things. Number two, I would recommend put in further losses, add environmental losses. You can add some sort of values for those, and it will basically incorporate in simulation. Coming to the practical, because you cannot do a lot of things in simulation, there are a lot of limitations when you work on simulation. But when you come to the practical zone, you can basically make a lot of changes in the environment around to come to the ideal situation as close as possible. So when you place an antenna inside a chamber, make sure you use proper RAM around the structure that basically holds the antenna. It's not large enough, or it's not very big that it is going to affect your measurements. Make sure basically when you put something inside the chamber, you have to specify its exact location and everything. Be specific, be to the point. Like, for example, if it is at 12.56 meters, specify it as 12.56 instead of just saying 12.5. These minute details affect a lot in terms of measurements. So uh, you stay as detailed as possible. That will help you minimize the difference between simulation and practical. But obviously, it will never be a perfect match. There will always be some sort of differences because it's impossible to achieve an ideal situation. And at the end of the day, your antenna will not be used in an ideal situation as well. So you can plan your simulations accordingly. You can plan your structures accordingly. In simulations, what you can do is you can put some sort of material around it. So for example, I know when I put something inside the chamber, I'm going to use a 3D printed support structure. What I do is I do a final measurement where I place a 3D printed support structure around my antenna and again measure it, and it gives me some sort of further losses which I can see inside the chamber, inside the anechoic chamber as well. So adding those sort of components to your simulation, it will help you achieve results much closer to the practical measurements. How does multi-frequency signaling antenna array suits for transmitting power to multiple points? So this is where another term called group velocity comes into picture. So every antenna has a particular group velocity that we need to consider. So at different frequencies inside an antenna, the group velocity will vary. And if at different frequencies, the difference between the group velocity is very high, it is going to create some sort of problem for in your antenna. And if so, for example, in my antenna, if I plot a group velocity, it varies from 0.6 times of speed of light to 0.65 times speed of light, which is not very high for the whole frequency band. And hence, I can use any frequency band from 27 to 31 gigahertz. But at the same time, if my group velocity changes from zero point 0.4 at 20, zero point 0.4 times of speed of light to zero point 0.8 times of speed of light throughout the frequency band from 27 to 31, it is going to create a lot of problem when I feed two different signals inside my antenna. So when you design multi-frequency antenna, this is something that you need to consider how the group velocity of of your antenna is being changed. For SIWs, there is a very simple way of measuring it. We measure group velocity within a waveguide. It's a similar equation. It's just we upgraded for assuming that instead of having air inside like a normal waveguide, we have substrate inside, and we add the effects of dielectric in it. Which is the best substrate material suitable for operating under 6 gigahertz and millimeter wave range? So under 6 gigahertz, you can use any material really. You can use RT5880, 5870, or TLP5, FR4. FR4 is generally the most lossy one. So in practical applications, we do not use FR4 a lot. I would recommend you stick with RT5880. That is one of the best. I personally use TLP5 or RT5880. Both are exactly the same material, but from different companies. TLP5 is from Teconic. They provide free samples. I use a lot from them. Like the company has a contract with my university, so it's easier for us to acquire that material. But in India, RT5880 is much more easier to than Teconic because Teconic comes from France. RT has their production in India as well. So at millimeter wave ranges, RT5880 is one of the best suited materials. Other than that, if you go to Rogers' website, Rogers Corporation, they have introduced a lot of new materials for 28, 30, 60 gigahertz frequency bands, which are these materials are specifically designed for these frequency bands. So if you can get hold of these materials, that will be amazing. Any other questions, guys?
Vijayalakshmi ma'am.
Sir, thank you so much for your nice presentation, sir. It was very much useful for us.
Thank you, ma'am.
So, Dinesha, Reshma,
Thank you, sir, for your really given us all a valuable and wonderful session. Thank you all. The link for the feedback form will be posted. All the participants are asked to fill it out. Only those who fill the feedback form will get the re-certificates. I repeat, only those who fill the feedback form will get the re-certificates. The form will be active only for 15 minutes.
Aakash
Collective
sir.
work is the secret behind the progress. Thank you is the progress that has to be felt by heart. Now let me invite, it will be Dinesh, IEEE APS Staff Advisor, Associate Professor, ECE Department, to deliver the vote of thanks.
Nityavadi ma'am?
Sir, I need to say one or two lines about
Yes, ma'am.
Aakash
You
sir.
can go ahead,
Can
ma'am.
I take the session? Yeah,
Yes,
thank
ma'am.
you,
Yes,
thank
ma'am.
you. Akash sir, I got your number from Ramni Kalra, and we were seeing your resume. It was very fantastic, and I need to share the resume with my students. Can I do that? And also, uh, your work, your research, it was very great, and indeed we are very privileged to have you with us, sir. Could you give a helping hand to us in our future research work or collaboration work? Are you willing, sir?
Thank you so much, ma'am. Yeah, you can share my resume and we can always discuss what work you're doing and how can I help. I'll be happy to help in any way possible.
Oh, thank you. That's great of you, sir. Thank you, sir. Thank you so much. Dinesh, sir, you can go on with the session. Thank you.
Yes, ma'am. Yes, ma'am. Good evening to all present here. I'm very glad to present the vote of thanks in this occasion. So first of all, I thank the IEEE Madras section and the IEEE Madras chapter, APS chapter, Chairman Dr. T. Shanmuganathan, Department of Electronics Engineering, Pondicherry University, and IEEE APS Madras chapter Secretary Dr. Joseph Gladwin, sir, Professor EC, SSN College of Engineering, Chennai. So the IEEE APS Madras chapter is accepting all the proposals which we have organizing for the past 2 years and all. And thank you for the IEEE APS Madras chapter and the organizing members there. Next, I thank today's speaker, Mr. Aakash Bansal, PhD Research Scholar, UK. So, Sir has given a nice overview about the 5G millimeter wave antennas. So, I think most of the participant students and the faculty members who are working in this field would have got an idea to start a research, and those who are working in this area will be getting some inputs in order to take over their research over there. And next, we also thank Dr. G. Murugesan, sir, Professor EC, Congo Engineering College, and our HOD, Dr. T. Meera Devi, ma'am, Professor EC, Congo Engineering College. So, for supporting us and all the times for organizing such an event to our students. Next, I thank our KSA IEEE Student Branch Counselor, Dr. T. Nityavadi, ma'am, Congo Engineering College, who helps us in every event and encouraging us in all the dimensions in order to organize such a kind of webinars and workshops and all. Thank you, ma'am. Finally, I thank all our IEEE APS student members, especially to the IEEE APS student chair, Snega, and vice chair, Sridharan. So, who had worked behind the screen to make this webinar a great success. Thank you all once again. Thank you, Aakash, sir.
Thank you so much. Thank you everyone for being here.
Thank you, Nityavadi, ma'am.
So thank you everyone of this team, and I personally and professionally thank IEEE APS Madras section for sponsoring this seminar series, and it was a very nice presentation by our first speaker of the 6 days program. And I thank the participants for patiently listening, and many queries are being sent to the mail also, so we will reply to that mail. And thank you so much. With this, we are closing the session. Joseph, sir, thank you, sir. So we are officially closing the session, right?
Yes, ma'am. Yes, ma'am.
Okay. Thank you, everyone.
Thank you to all.
Thank you, everyone.
Thank you, sir.
So, will you
Participants?
please send the
Yeah.
feedback link once again?
Yeah, I will post it now. Participants, kindly fill the feedback form which is being posted in the chat window. So those who fill the feedback form, we will provide the e-certificates.
For your kind information, the form will be active for 15 minutes. Thanks to everyone.